Alright, let's start with this idea of combining operations research, which I will keep calling OR, and machine learning or ML. Now, OR is really about using mathematical optimization and decision science to solve complex systems. You might have heard of things like linear programming or nonlinear programming, where we try to minimize or maximize some objective under constraints. And OR also covers resource allocation problems, network optimization, and decision theory, which is basically how to make rational choices under uncertainty. On the other side, we have got machine learning, and ML is more about data-driven algorithms that recognize patterns, learn from data, and make predictions. Things like predictive modeling, feature learning, handling uncertainty, and of course pattern recognition fall into this area. So while OR works with precise models and constraints, ML works with messy real-world data. So why even bother combining these two? Well, look at this. The strength is in what each one brings. Machine learning can give us data insights like predicting demand. Then OR can take those predictions and optimize the actual decision, like how much inventory to order. Together, that means better decision making. Another reason is dynamic optimization. ML keeps learning in real time, while OR ensures that whatever decisions we make still respect the constraints. And the third reason is about solving complex problems. Combining the two lets us manage uncertainty but still aim for optimal solutions. And of course, both have their limitations. OR needs problems to be formulated very precisely, and it often assumes parameters are known, which in reality is not always true. It is not so adaptable when new data comes in, and it doesn't handle uncertainty that well. ML, on the other hand, doesn't guarantee optimality. A model might give predictions, but there is no guarantee it's the best possible solution. Also, it can act like a black box, ignoring constraints, and it usually requires large datasets. So, how do we overcome this? The answer is what you see here, synergy. ML can learn the parameters, OR can then optimize the decisions. OR provides structure and ML brings flexibility with uncertainty. When you put them together, you get systems that are both optimal and adaptive. Okay, and let's continue. Integration approaches is here. So, here, actual integration approaches. The first one is called predict then optimize, and here the idea is simple. You use ML to predict key parameters like demand and then pass those predictions into an optimization model. For instance, if we can forecast demand more accurately, we can fit those values into an inventory optimization model to decide stock levels. And a second approach is embedding ML inside our models. That's when you directly replace uncertain or nonlinear parts of the optimization problem with ML surrogates like neural networks acting as constraint functions. The third approach flips the things around a bit, or guided ML. And here we bring optimization principles into ML training. For example, you might constrain a neural network during training so that its outputs always satisfy certain feasibility conditions. And then we have reinforcement learning combined with OR. In this setup, RL agents learn by interacting with an environment, but the OR constraints are built into the system, so the learned policy respects them. That's very powerful problems like resource allocation with learning agents. And let's look more closely at the predict then optimize approach. You can see here there are usually four steps here. First, you collect historical data. Second, you train your ML model to make predictions. Third, those predictions are used as parameters in an optimization model. And finally, you solve the optimization problem to get decisions. So you can see it's a pipeline: data, prediction, optimization, decision. Okay, let's continue. And let's see this in action through a case study. What is that? Smart inventory management. The example here compares traditional fixed order methods with a combined ML and OR approach. So we can adjust three main parameters in this simulation: demand variability, which is currently set at 50. Inventory cost, here it is $3 per unit, and stockout cost set at $25 per unit. Demand variability represents how unpredictable demand is from week to week. Okay. Inventory cost is a holding cost of keeping extra stock, and stockout cost represents the penalty or loss opportunity when demand cannot be met. And after we run the simulation, the system generates weekly data, you can see here. And what we see in the graph is a cost comparison. And let's look at this. The red line is a traditional approach which orders a fixed amount each time. The purple line is the combined ML plus OR approach, which adapts orders based on predictions and optimization. And you will notice the purple line generally stays below the red line, showing cost savings. And if you look at the totals, the numbers back it up. The traditional method gives us a total cost of $756. The combined ML and OR method reduces these to $495. And that's a savings of $258 across the simulation period. So the point here is clear. By combining ML forecasting with OR optimization, we can make smarter, cheaper decisions compared to traditional fixed rules. And this example might be simplified, but it demonstrates the value of OR and ML's synergy in real operations. And let's try other parameters like that and that and that. Run simulation again. And here you can see. And remember, it's only an example. So, real world applications here. What are they? Let's look first up: supply chain and logistics. Here the OR side focuses on things like network optimization and routing. For example, how to move trucks or containers in the most efficient way. And the ML side brings in demand forecasting and disruption prediction, like estimating future orders or anticipating delays due to weather or strikes. And when you put the two together, you get adaptive supply networks. And that means not only choosing optimal routes, but also adjusting them based on predicted demand. Example applications here include dynamic vehicle routing, predictive inventory management, and risk-aware logistics. And healthcare operations. Here, OR helps with resource allocation and scheduling. So things like nurse rostering or making sure operating rooms are used effectively. ML helps with predicting patient outcomes or assessing in diagnosis. If you combine them, hospitals can both plan resources optimally and anticipate patient needs. And that's useful for ICU capacity planning, scheduling surgeries with expected outcomes in mind, and even emergency response optimization. So, finance part. On the OR side, we have portfolio optimization and risk management, essentially balancing return and risk under mathematical constraints. The ML component adds market prediction and sentiment analysis, meaning it can process large streams or financial data or new sentiments. Together, this synergy allows us to optimize portfolios while considering learned market patterns and constraints. You will see applications like robo-advisors, algorithmic trading, and credit risk optimization. Energy part is here. Here, OR is about grid optimization and capacity planning, how to distribute power across the network efficiently. ML adds load forecasting and renewable prediction, for example, predicting wind or solar generation. Combine them and you get smart grids that optimize energy distribution while also anticipating demand and supply changes. And that translates into practical applications such as smart grid management, renewable energy integration, and demand response optimization. So, before we wrap this section, I want to show you some of the mathematical frameworks that tie these ideas together and predict and optimize. And the formula looks like this. What is that? Y hat equals f of ml of x. Then we solve the optimization problem, minimize c of y hat transpose times c subject to a z less than or equal to b. So the ML model predicts parameters and then OR solves the decision problem. End-to-end learning, here the formula is here, minimize expectation of c of x epsilon transpose z star of f theta of x plus lambda r of theta. What this means is that the ML training objective already includes the optimization costs. So the model learns directly with the decision making in mind. And the third is reinforcement learning. The formula is here. What is that? Pi star of s equals arg max hour of expected reward given state s and action a subject to g of s a less than or equal to 0. In simple terms, the RL agent chooses the best action but has to respect optimization constraints. So these mathematical frameworks give us a structured way to bring OR and ML together. They are like the backbone of all the real-world applications we just talked through. And thank you for listening.